Today I want to provide an overview on explainable AI. I'm not going to provide information about everything because it's a rather big area, but I will be concentrated on a few techniques which I will be utilizing in my final project. So while the first AI systems were easily to interpret and built on subject matter, today modern machine learning systems work quite in the opposite way. It generates their own presentation purely from the data and construct their representation of the world of this world from that. So one notable example of such a PAC decision system is deep learning, which empirical success actually stems from a combination of efficient learning algorithm and their huge parametric space. And from this figure, you can see that neural networks actually has a very good performance, but very bad explainability. So this machine learning evolution resulted in a growing number of papers regarding explainable AI, and this area of research actually blooming since 2016. So the new machine learning system should have the ability to explain its rationale, characterize its strengths and weaknesses, and convey an understanding how it will behave in the future. So one example of a model-specific explainable AI system is the convolutional network. It's basically a mirrored version of a convolutional network, and it has multiple series of unpooling, deconvolution, and rectification layers, which identify pixel-wise class levels and predict segmentation masks. So the unpooling operation is not complex to understand. It records the locations of maximal activations selected during pooling operations, and then place each activations back to its original pooled location. So this unpooling strategy is practically useful for to reconstruct the structure of an input object. So the output of unpooling layer is an enlarged and sparse activation map, and the deconvolutional layer then densify the sparse activations obtained from unpooling layer through convolution-like operations with multiple learned filters. So the output of the convolutional layer is enlarged in this activation map. So here you can see some visualizations of activations in the convolutional network, where the image A is an input, and the rest are the outputs of the last deconvolutional layer. So the final details of the objects are revealed as the features are forward propagated through the layers in the deconvolutional network. So the noisy activations from background are suppressed through propagation, while the activations closely related to the target classes are amplified. One example of the model-agnostic explainable system is a local-interpretable model-agnostic explanation system, or LIME. So the core idea behind LIME approach is not very complex. So for every classifier with highly nonlinear decision boundaries, there is always exists some locality which could be explained by simple interpretable linear model, but it could be any simple model, it could be linear regression. Thus, LIME uses a local surrogate model trained on perturbations of data points, which is then instigated for explanations. So this ensures that even though the explanation does not have global fidelity, it should have local fidelity. Or in other words, features should be important in the local context. So this method uses under the hood, it uses interpretability versus fidelity trade-off function. And It looks rather complex, but basically it tells that in order to ensure both local fidelity and interpretability, we need to minimize the unfairness or maximize the local fidelity. And we need to also keep in mind that complexity should be low enough for humans to understand. So in this formula, we need to maximize L function, and while the complexity, which is omega, should be pretty low. So the algorithm of this method follows these steps. So it samples the locality around the selected single data point, or it could be pixels, which forms the superpixels, and random, and generate a data set of perturbed data points with its corresponding prediction from the model, which we want to explain. And then it calculates the sample weights to represent how close or far away the sample points are from the original point. And it fits the interpretable model on the perturbed data set using the sample weights to weigh the objective function. And then it provides the local explanation using some simple explainable model like linear regression. So as an example, you can see that when it is applied to the image processing, it actually creates a group of superpixels, which then could symbolize different decision points, and it can actually explain how the different objects of the image forms the decision of overall model. Thank you.